Section 11.5 Alternating Series. An alternating series is a series whose terms are alternately positive and negative. It turns out that there's a test to determine whether an alternate series converges. The test requires that the series is decreasing, but when we say decreasing for an alternating series, we mean that the terms without the minus sign are decreasing. So what we do is we use this notation Bn, where An is the entire term, including the potential minus sign, and Bn is the term without the sign. So if the sequence is like 1 minus a half plus a third minus 1/4, etc., you can see it's alternating because of the minus signs on half the terms. But when we consider whether it's increasing or decreasing, we only consider the B terms, which means we consider the 1, the half without the minus, the 1/3 without the, well, with the plus it doesn't make a difference, and the 1/4 without the minus. So in order to see if an alternating series converges, we need that condition satisfied, but we also need that the limit of all of those terms is 0. So let's prove this. First, take a look at this picture right over here. We're assuming that we have these two conditions, and we're assuming that our series alternates. Given that, if we look at the first term starts at 0, let's say, and then it goes up to a certain amount, whatever the first term is. But then it goes backwards a certain amount, because the next term after that has to alternate and become minus of whatever the first term was. Well, not whatever the first term was, but up to whatever the first term was, but not quite equal to that much, because remember, the terms are decreasing. So that means that when we subtract and we go backwards for the second term, there's no way that we could go past where we were for the first term, because the value of B2 is less than or equal to the value of B1. So that means that the sum of the first two terms will always be a positive number past where we started. And that means that the sum of the first 4 terms will be a positive number even past that, because you just do the exact same thing again. You go forward B3, and you will not get as far, or you won't get past where you were at the first sum, because B3 is smaller than B2 by our assumption. So you keep doing this, and you can see that the sum of the first 2 terms will be before the sum of the first 4 terms, which is before the sum of the first 6 terms, etc. So we can write that out as S2 is equal to the first term plus the negative of the second term, because negative B2 is the second term, it's alternating. And then we can see the sum of the first 4 terms is the sum of the first 2 terms plus B3 and then minus B4. And then that'll be past S2. It'll be greater than or equal to S2. So in general, we can say that for the even terms, the sum of the first 2n terms is equal to the sum of the terms 2 back from that, plus the next two b's, the difference between them. So that means that in general, as we said, these guys are all nested, where each even term that comes next is greater than or equal to the previous one. However, by definition, we can also write that the sum of the first 2n terms is just the sum of the terms in the sequence. The first term of the sequence is B1, then there's minus B2, then plus B3, but instead of writing plus B3, I factor out the minus over here, so that I can group these differences together. Do the same thing, keep going. We'll subtract B4 because that's the next term, then plus B5, and so on. We keep doing that, and that's just exactly how we construct a partial sum. It's just adding up all the terms that came before. So then notice that all of these terms in parentheses, those are all these differences over here. It's like B2 minus B3, that's like this difference over here, and then this difference over here, etc. Those are all positive. So because all those are all positive, that means that we have that the sum of the first two n terms is less than or equal to b1 for all n. You can even see that if you look over here, b1 takes you all the way over here. So each of these s2s all the way through whatever are always going to be smaller than that. So we have a sequence of partial sums that is increasing and bounded above. So it must be convergent by the monotonic sequence theorem. So that means it has some limit. We can say s. So we'll say the limit of all of the even terms is s. Now let's look at the odd terms. The odd partial sums, I mean. So if we take the odd partial sums, we could write that limit as the limit of the even partial sums plus the next term that comes after that makes it odd. Well, the limit of the even partial sums we just said was s, and the limit of the odd partial sums was just the limit of bn. And remember, we are assuming that bn is 0, so the limit of bn plus 1 is also 0. So that means that this limit of the odd partial sums is exactly the same as the limit of the even partial sums. So they both converge to the same limit. So that means that the limit of the partial sums in general converges to the limit, and we have our series converges. So let's determine whether this alternating series converges or diverges. This is the alternating harmonic series. Notice the only difference between this and the harmonic series 1 over n is that we have minus signs on half of the terms. So let's see if we satisfy the first condition of the alternating series test. We need to look at the next term in a sequence. So if 1 over n is one term, then 1 over n plus 1 is the next one. Remember, we look at bn's, which means we do not look at the sign. We only look at the term without the sign. You could think of it as the absolute value of the term. So this is definitely going to be smaller than 1 over n because it has a bigger denominator. So that means that bn plus 1 is less than or equal to bn. So our series is decreasing. And we look at our second criteria. We need the limit of the bn's to go to 0. Well, the limit of the bn's is just the limit of 1 over n. So that is 0. So we satisfied both conditions. We have an alternating series. That means that the sum of our series an converges by the alternating series test, which is pretty interesting because if you remember from the harmonic series, we looked at a few different reasons why the harmonic series would diverge. It's a p series with p equal to 1, and we did our proof where we looked at the 2 to the n partial sums. But it turns out that if we throw in a minus 1 to the n minus 1 and force the series to alternate, then that makes it converge. So some series we're going to look at when they have an alternating version of themselves will actually end up converging. Let's determine whether this series converges or diverges. We have a little bit of an issue here though. Notice that for our second condition of the alternating series test, we need the limit of the bn's to be 0. But in this case, the limit of the bn's is the limit of 3n over 4n minus 1. Remember, we only consider this part. The entire thing is an. Without the sign, it's bn. So this is the limit of 3 over 4 minus 1 over n if we just divide by n. And that's just 3/4, which is not 0. Since the limit of bn is not 0, we can't use the alternating series test. So let's see if we can figure out if it diverges some other way. Well, how about we take a look at the limit of the an's. Remember, this is not going to be the sum of the series. We need a limit of Sn to converge if we want the sum of the series. However, just taking the limit of ANs is one of our tests. If we take the limit of minus 1 to the n times 3n over 4n minus 1, then we could separate the limit, get the limit of minus 1 to the n times the limit of 3n over 4n minus 1. Now, we know that this limit does not exist. However, you have to be a little bit careful here. You can't just stop at that point, because remember, for our alternating harmonic series, we knew that that limit also doesn't exist. But this thing ended up converging. So we should investigate the limit that remains, like the limit 1 over n over here. That did not converge. This thing did not converge, but somehow multiplying them together made an indeterminate form which converged. So over here, let's take a look at this limit. Well, that's just going to be the limit that we get when we divide the numerator and denominator. So that's just 3 over 4 minus 1 over n. So this limit is just 3/4. So this thing just becomes 3/4 times the limit of minus 1 to the n. And that definitely does not exist. Remember that minus 1 to the n just oscillates back and forth infinitely often. Multiplying it by 3/4, that just doesn't change anything. It's still going to oscillate just from minus 3/4 to 3/4. Now remember that even though the limit of the ANs is not the sum of the series, the limit of the ANs must be 0 in order for the sum of the series to exist. Otherwise, our series diverges by our test for divergence, aka our nth term test, because we took the limit of the nth term and we saw that that doesn't go to 0. So our series never levels off. So even though we had an alternating series, we couldn't use the alternating series test. You won't always be able to use it on every alternating series. And that doesn't mean that you can't test it, we just had to use a different test. Okay, how about this series? Well, it definitely alternates. It's not clear whether the terms are decreasing though. So how about we take a look at a corresponding function? Because we do have some calculus tricks that tell us when functions are decreasing. So if we look at the function x squared over x cubed plus 1, then we can look at the derivative. And using the quotient rule, we get that that's x times 2 minus x cubed over x cubed plus 1 squared. Let me just do a little simplifying. So that's going to be negative when this guy is negative, because remember we're starting at n equals 1. Slight typo over there. So that means that we're not considering any negative values for x, so there's no danger of this being negative, and this is squared, so no danger of that being negative. So we only have to worry about this being negative. So that means that we want to see when this thing is negative, which is when x is greater than the cube root of 2. So that means that our corresponding bn's will be decreasing because our function is decreasing. And that's so long as we have n greater than or equal to 2. Remember, our alternating series test said it needed to be true for all n, but we can relax that criteria a little bit because we only need to consider the ending terms in a series in order to test for convergence or divergence. If we have a finite number of terms at the beginning, they will not affect the convergence or divergence of a series. Although in this case we could actually see that the b1 will actually be less than b2. We could test that ourselves, but it's okay, it doesn't really matter. So this means that we have condition number 1 satisfied. So let's look now at condition number 2. For our alternating series test, we need to take the limit of the bn's. So that's the limit of n squared over n cubed plus 1, which is just the limit of 1 over n, because we're divided by n squared in the numerator and denominator, over 1 plus 1 over n cubed. And that's equal to 0 because, notice this thing goes to 0, and this thing goes to 0, so we get 0 over 1, which is 0. So we can use the alternating series test and say that this thing is convergent. It passed. So it turns out that the alternating series test is not the only special thing about alternating series. If you have an alternating series that passes the alternating series test, then that tells you something about the remainder, assuming that you approximate your alternating series using a partial sum. It tells you that the difference between your actual sum and your partial sum must be less than or equal to the first term that you leave out. For example, if I added up the first 10 terms in an alternating series, then how far off I am must be less than the 11th term. So that's pretty cool. We know from the proof of the alternating series test that our sum lies between any two consecutive partial sums, because we showed that s is larger than all of our even partial sums, and we could also show that s is smaller than all of our odd partial sums. So that means that depending on whether Sn and Sn minus 1 are even or odd, we either have that Sn is less than or equal to s, which is less than or equal to Sn minus 1, or we have that Sn minus 1 is less than or equal to s, which is less than or equal to Sn. So what we can do is subtract Sn from all the sides over here and over here. So we either get that s minus Sn is less than or equal to Sn minus 1, or we get that s minus Sn is greater than or equal to Sn minus 1 minus Sn, Sn plus 1 minus Sn. I wrote minus 1, I should write plus 1 over here, but it doesn't really matter. So we end up getting rid of we want to try to combine these two into one inequality, so we just put absolute value. And that basically tells us that if the difference is positive over here, then it's less than or equal. If the difference is greater than or equal for this one, then it's just negative version of the first one. So to accommodate for both, we just throw an absolute value in there. So that forces this thing to be true. But notice that the difference between Sn plus 1 and Sn is literally just the next term, Bn plus 1. So let's do an example of this. How about we find the sum of the series minus 1 to the n over n factorial, correct to 3 decimal places. So let's just do our alternating series test really quick. We've got 1 over n plus 1 factorial. I want to show that that's smaller than 1 over n factorial. Notice though that if I have like, I don't know, 1 times 2 times 3 times 4 times 5, then this is equal to 5 factorial. So this first part without the 5 is equal to 4 factorial. So really you could say 4 factorial times 5 is 5 factorial. In general, you could say that if you're multiplying 1, 2, 3, and so on, all the way up to n and then n plus 1, and that's n plus 1 factorial. What you could do is just pull out the n factorial that comes before. Just write it as n factorial times n plus 1 equals n plus 1 factorial. If you pull off that extra term at the end, then you're left with the previous factorial. So let's do the exact same thing over here. That way we have an n factorial outside of the n plus 1 factorial, and we'll be able to compare this to 1 over n factorial more easily. So we rewrite this as 1 over n factorial times n plus 1. And that's definitely going to be actually smaller than 1 over n factorial because it's got a bigger denominator. So now we'll just have to take a look at our second condition for alternating series test. So we have that 1 over n factorial is less than 1 over n, right? Because we're multiplying by a ton more stuff in our denominator and for 1 over n factorial. But we already know that 1 over n tends to 0 as n tends to infinity. So that means that 1 over n factorial definitely tends to 0 as n tends to infinity. It gets even bigger in the denominator. Okay, so that means that our sum converges by the alternating series test. Now that we know that our sum converges, let's try approximating it using a bunch of terms. We need to do it to 3 decimal places, but we don't know how many terms we need. So let's just write out a whole bunch and see when we get to the next term being 3 decimal places. So 1 over 0 factorial, because we're starting at 0. And remember, 0 factorial is 1, so there's no issue here of dividing by 0. And then 1 over 1 factorial, 1 over 2 factorial. Should have a minus over here for this next one because it's alternating. 1 over 3 factorial, 1 over 4 factorial, minus 1 over 5 factorial, plus 1 over 6 factorial, minus 1 over 7 factorial. 7 factorial is pretty big though, so how about we stop there and take a look at what these equal. This is 1 minus 1 plus 1/2 minus 1/6 plus 1/24 minus 1/120 plus 1 over 720 minus 1 over 5040. So that means that if we look at this 7th term, B7, without the minus sign, that's 1 over 5040. Oops. Which is even smaller than 1 over 5,000, which is just 0.0002. So it looks like we're at the 4th decimal place, so these first 3 should be good. So if we look at the sum of the first 6 terms, 1 minus 1 plus 1/2 minus 1/6 plus 1 over 24 minus 1 over 120 plus 1 over 720, then that's approximately 0.368056, and the error involved, s minus s6, which is our partial sum for 6 terms, must be less than or equal to B7, which is 0.0002. So it has no effect on the first 3 decimal places. So that means that our first 3 decimal places of S6 must be accurate. So we have that our sum of our series accurate to 3 decimal places is approximately 0.368.